All right, here we go, our last lesson of the school year. So you can celebrate that this is our last set of geometry notes that you will ever take. You should have gotten a text message from me with this question. There are 33 students in this class. Don't turn around and count right now because some classes have 33, some have something different. But let's just assume there's 33 students in the class. If everyone shakes hands with everyone else, how many handshakes were there? This question very creatively, hopefully you're hearing the sarcasm there, is called the handshake question. And by the end of the lesson, you should be able to answer this question. The more general idea that I want you to think about with this question is I want you to think of this in terms of connectivity, in that everyone in the class is going to connect to everyone else in some way. That idea is a crucial idea for this question, and as we work through the lesson today, I want you to be thinking about which formula that we cover would allow us to understand everyone connecting with everyone. Where do we find what we would call total connectivity? So in order to get there, we're going to jump into our notes. So we're going to be on page 8 of your notes, and we're going to start with some patterns that are going to seem a little bit strange, but they're going to directly relate to the previous two lessons. So the first question that we're going to look at is how many diagonals can be drawn from just one vertex of a 20-gon. And what we've learned so far in writing these patterns is that we don't want to have to try to draw a 20-gon. So instead, we're going to think about smaller polygons and build our way up looking for a pattern. So when I look at my three-sided polygon, my triangle, I can see that if I pick a vertex, just a single vertex, and I try to draw in the diagonals, there are no diagonals that I could draw. So when I come down here to my pattern, I'm going to find my three-sided polygon. Don't worry about these, I'll address them in a moment. Three-sided polygon, and I can see that there are 0 diagonals there. Now, I've drawn in our next one for us. So what I've done is I've chosen this as my vertex, and I can see that there is 1 diagonal that I could actually draw in there. So I get 1 diagonal in my quadrilateral. And you can see these ones have already been drawn in as well. I chose a vertex for you. You could have chosen a different vertex, and you can see that I have 2 diagonals that I can get in my pentagon. And you might be able to predict what this next one's going to be even without looking at the picture. But again, I've chosen a vertex for you, and I've drawn in the diagonals for you, and I can see that there are 3 diagonals in that polygon when I choose a single vertex. Now, if I build on that, okay, I can see the pattern that is happening. My pen is kind of dying here, sorry guys. Okay, so I can see the pattern that's happening here, but when we write our rules, we really want to have a rule that starts with an n value of 1 that's going to be easier for us. So although we know that there's no such thing as a polygon with 1 side or a polygon with 2 sides, we can put lines through those. We know that logically in our head that those physical polygons don't make sense. What we can do is we can extend this pattern backwards. We're accustomed to extending it forwards, but we can go backwards as well. So what we can see on this particular pattern is we can see that we're actually going up by 1. So our common difference, our rate of change, is a +1. So if we want to go backwards, we're going to subtract 1. So at n equals 2, we should have a value of -1, and at n equals 1, we should have a value of n equals 2. So we can see that we have this common difference of 1. Again, think rate of change. So if we want to write this rule, the first thing that we should notice is that this is one of our linear rules. Okay, so this is one of our linear patterns. And when we have our linear patterns, we know that we're going to take our common difference and write it as our slope. So we're just going to have a 1n, or in our case, just an n. And then remember, we take the difference of these two. So we're doing a -2 minus a 1 to get our -3. So that gets our rule to predict the number of diagonals from a single vertex. we can then use that rule to find f of 20. So you can quickly plug that in. We're going to put our 20 in for n, so we're going to have 20 minus 3, and that gets us 17 diagonals in a 20gon when they're drawn from a single vertex. Okay, so that's our first type of connectivity. We have one person, one location that's going to connect to the other diagonals there. Okay, now moving on down, we're going to have all the diagonals. Now this is going to be different because on this one we chose a single vertex and connected it only to the vertices that were across from it. Okay, notice that we did not connect this vertice to the vertices that were next to it. We only did it to the vertices that were across. So if we think of this as people, okay, we have this person and they're going to reach across the group, but they're not going to reach side to side. Down here, for if we want to do all the diagonals, okay, we're still going to have people reaching across, but we're still not going to have people reaching side to side because we're specifically looking at diagonals. We're going to have the same idea that we need to look at here because we're thinking polygons just like before. We know we're not going to have a one-sided polygon. We know we're not going to have a two-sided polygon, but we will be able to work backwards in a moment to fill those in. So let's jump to our three-sided polygon, our triangle. We can see that there are no diagonals, so we can put in our 0. When we come to our quadrilateral, I've drawn in one diagonal for you, but now I want to draw in the remaining diagonal. So we can see on our quadrilateral, we'll get 2 diagonals. On our pentagon, just like before, I've drawn in these 2, but we need to also draw in our other ones. So I could draw in this diagonal right here, and then I can also come in and I can draw in these diagonals. So it looks like a little star there, and if I count those up, what I'm going to find is that I have the 2 blue, the 2 red, and the purple, so I have 5 diagonals. When I get to my hexagon, I've got my 3 diagonals here. Then I can draw, I'm going to pick another vertex, and I can draw in some more. So I'm going to get 3 more there. My purple pen is definitely dying. And I can go to another vertex here. So I can draw on this one. I don't need to redraw that blue one. I can draw on that one. And then I've got just a little bit more to go. I've got my diagonal right there as well. I don't need to reconnect that one. I don't need to reconnect that one. So if I count all of those up, what I will find is that I have 9 diagonals drawn into that figure. Now, when we look at this pattern, first of all, don't worry about these 2 spots right now. When I look at this pattern, what I can see is that I've gone up by 2, and then I went up by 3, and then I went up by 4. Okay, so what I know is this is not linear. I can definitely see that it's not linear because we are not going up by a constant rate. However, if I look at the difference of my differences, what I can see is that if I have a constant second difference, we talked about this last time, and my constant second difference is 1. So since I have a constant second difference, I know that this is quadratic. So it is our quadratic pattern. And not only is it quadratic, we need to recognize that we have an odd second difference. Because as you remember last time, the odd second differences created a triangle pattern, so we're going to have to do something special with that. So now, before we can jump into actually working with our quadratic odd pattern, what we need to do is we have to remember that we have to extend this backwards so that we can fill in these 2. So remember, if this was doing 2, 3, 4, then this must have been a +1, and this is going to be kind of weird for us to look at. this difference is going to be a 0, because remember, this has to create that nice pattern so that these will have a +1 difference and these will have a +1 difference. Okay, so we're going to work backwards. So these need to have a +1 difference, so I'm working backwards. This should be a -1. This difference is supposed to be 0, so I'm going to fill in another -1. Now, it seems kind of strange that we have these same numbers, but we actually saw something similar to this before. Now, from last time, what we know is that on a quadratic pattern that's odd, the very first thing that we have to do is we have to double this. Remember, we're thinking about taking our triangular pattern and turning it into a rectangle. So we're going to double all these. So we have our -2, a -2, a 0, a 4, a 10, and an 18. Okay? What we're trying to do, remember, is we're trying to develop a formula that will allow us to predict the number of diagonals in any type of polygon. Now from here, this is a little bit of a review from last time. We want to write out our factors. Remember, these ones are usually the harder place to start. So we don't usually want to start with our negatives or our 0. So we're going to start with our positive numbers here. These are going to be the easiest spots. And I'm going to let you write those out. Remember, when we write out these factor pairs, we always want to write the pairs low to high. So I'm going to have my 1, 4 for my 4. I'm going to have a 2, 5 for the 10. And for my 18, I'm going to have a 3 and a 6. Remember from last time, we certainly could have written out more patterns there. I'm kind of jumping ahead because you've already done your homework, so you've already practiced this idea. Now, what we want to recognize is that these low numbers in each pair are creating a pattern. So I have 1, 2, 3, or think backwards. I have 3, 2, 1. That means this is going to become a 0. Go backwards again. This is going to become a -1. And this is going to become a -2. So just extending the first number backwards. Just a little review of last time. Now, if I look at the second number in each of these pairs, I have a 4, 5, 6, or think backwards, 6, 5, 4. That means that this should be a 3, this should be a 2, and this should be a 1. Now, if our pattern is correct, I'm going to do a little bit of color coding here. If our pattern is correct, then this product should give us a -2, and it does. This product should give us a -2. This product should give us a 0. So we know that our numbers are right. The next thing that we're going to do, or I should say the last thing that we're going to do here, is we're going to write our rule. So we're going to write our function rule. Remember, we're going to look at the first terms. That's going to create a linear pattern. Its common difference is a 1. So I'm going to have my n. And then we can write this down. This difference is a 1. So -2 minus 1 gives me a -3. The second pair, number in each factor pair, it also has a pattern of increasing by 1. So I'm going to have my n. And then, of course, 1 minus 1, first term minus your difference, gives me a 0, so I can stop right there. Now, this is the part that students do often forget. We talked about it last time. We wrote a pattern for these, a rule for this pattern of numbers, but these were not our original numbers. Our original numbers were half of those. So if we doubled in the beginning, we have to remember to take half when we finish our rule. So we can write ourselves a note. Don't forget to undouble it. I know that's not a proper word, but it's a good way to think about it. Don't forget to undouble. So this is our rule to find total diagonals. Okay, so if we want to know all the diagonals in a polygon. So back to the original question for this problem is how many diagonals would be in a 20-sided polygon. Well, now we can just evaluate our rule. So we're going to have our 1/2. We can do this in our head. 20 minus 3 is 17. And of course, just 20. You don't even need a calculator for this because half of 20 is 10. 10 times 17 is 170. So there are 170 diagonals. Obviously, nobody wants to write that out. All right, so we're going to pause this video. We're going to stop this one and let's ask some questions on this page. And then after that, we'll move on to the